So picture this. You've got two users miles and miles apart, and they're editing the exact same wiki document at the exact same time. They are totally unaware of each other. User 1 carefully types out a new title, wraps it up, and hits save. User 2? Well, they're doing the exact same thing, completely blind to what User 1 is doing. They both finish typing, and they both hit the save button at the precise same millisecond. They sit back, waiting that tiny fraction of a second for the safe to process, completely oblivious to the massive collision that's hurtling through the network. What does the database actually do with this? Does it just crash? Does it flip a coin? Or does it somehow magically combine their thoughts into one sentence? Let's break down exactly how this scenario unfolds under the hood. User 1 decides to change the document title from A to B and sends that update to their nearest database node. Let's call it leader 1. At that exact same moment, User 2 changes the title from A to C and sends it to their nearest node, leader 2. Because both of these users are just talking to their own local leader databases, both updates are instantly accepted as successful, right? The system doesn't make either user wait around for some global check because, well, that would cause insane lag. But because they sync asynchronously in the background to keep things fast, we suddenly face instant chaos. When these multi-leader databases eventually talk to each other to reconcile their data, boom, we have a massive collision. Leader 1 insists the new title is B. Leader 2 absolutely insists the new title is C. And obviously, they can't both be right. Okay, let's dive into this. Welcome to this explainer on handling concurrent writes and conflict resolution. Today, we're going to explore exactly how distributed systems solve this chaotic reality. We're going to dig deep into the mechanics of data reconciliation so that by the end of this, you'll completely understand the invisible, often super complex trade-offs your favorite apps make every single day just to keep things running smoothly when millions of people are online at once. Here is our roadmap for today. We'll start with Section 1, detecting concurrent writes. Then we'll cover 4 resolution strategies. 2, conflict avoidance. 3, last write wins. 4, manual resolution. And finally 5, automatic resolution.
Section 1, detecting concurrent writes. Defining the rules of time.
Before a database can actually jump in and solve a conflict, it basically has to act like a detective. It has to figure out if 2 operations actually collided or if one just simply happened after the other. To solve this little mystery, distributed systems rely on this absolute core mantra called the happens before relation. Basically, an operation A happens before another operation B if B knows about A, depends on A, or builds upon A in some way. It is so crucial to wrap our heads around the fact that in computer systems, concurrency isn't about literal time on a clock. It's entirely about causal dependency. Imagine user A posts a message and user B replies to it. User B's reply causally depends on user A's post. So B happened after A. Simple enough. But what if user A and user B both post a message to the same exact form at roughly the same time, completely unaware of each other? Well, those operations are concurrent. Even if one post traveled super fast over the network and literally hit the database a full 2 seconds before the other, they are still fundamentally concurrent because they didn't know about each other. They didn't build on each other. If neither operation happens before the other, they are concurrent. And when we have concurrent writes, we've got a conflict that needs fixing. Let's move to Section 2, strategy. Conflict avoidance. Stopping conflicts before they start. If we don't want to deal with conflicts, we need the absolute simplest, most brute force solution out there. We just arrange the system so that collisions literally cannot occur. This is conflict avoidance. If the app can make sure that all writes for a particular record always go through the exact same leader, well, conflicts become mathematically impossible. For example, you could route traffic so a specific user always connects to a home region based on where they live. From that user's point of view, the database behaves exactly like a single leader setup. No one else is touching their data on another server. So, the crucial point is, it works brilliantly until you look at the major flaw. It completely falls apart the second you have to change that designated leader. Imagine a massive failure where a data center goes offline, or even just a user moving across the country, and the system needs to reassign their home region so their app doesn't lag. During that switch, a user might suddenly be shunted to a new server, while their previous write is still kind of hanging out in the ether, unprocessed by the old failing leader. A concurrent write can so easily slip through during this geographical switch, causing the exact conflict you were trying so hard to avoid.
Section 3, strategy. Last write wins. The easiest, most destructive fix.
Okay, so if we can't avoid conflicts, we have to deal with them head on.
Last right wins is a strategy that absolutely forces the system to converge, but man, it does so at a steep price. Last right wins, or LWW, basically says that the write with the most recent timestamp is the winner, and all the other concurrent writes, they're just silently discarded, gone. But wait, think back to our happens before relation for a second. We already established that concurrent writes don't actually have a true sequential order. Because they are completely independent, they're happening in parallel, causally speaking. So picking one as the last write simply because of a timestamp, it's basically a random choice. It's kind of a philosophical absurdity to assign a definitive last to events that happened completely blind to one another.
Let's drill down into why this is so disruptive. Yes, last write wins gets us eventual consistency. Every single database replica will eventually agree on one value, which keeps the system online. But it achieves this at the cost of permanent data loss. The overwritten data is just silently deleted forever, even though it was successfully processed locally and the user was told everything saved perfectly. Plus, if you're using real-time clocks for these timestamps, your system becomes incredibly sensitive to clock synchronization issues. To put that into perspective, imagine a banking app. A user deposits $100 on their phone, which talks to a server with a perfectly accurate clock. Concurrently, an automatic direct deposit hits a different server, but that second server has a clock lagging behind by just a couple of seconds. Under last write wins, the bank's database compares the timestamps. The phone's deposit has a newer time, simply because its clock was running faster. So the database keeps the $100 deposit and silently, completely deletes the direct deposit. The money literally vanishes. Now, if your app only inserts unique records, maybe this strategy is fine. But if your application absolutely cannot afford to lose updates, like our banking example, this strategy is a total deal breaker. Section 4, Resolving Conflicts Manually. Storing siblings and passing the buck. If randomly throwing away user data isn't going to fly, the database can take another route. It can just throw its hands up, say, hey, not my problem, and force the application layer to sort the whole mess out later. The key concept to understand here is siblings. Siblings are all the concurrently written values for a given record that the database stores and returns together when there's a conflict. So instead of deleting title C to keep title B, the database saves both of them. The next time the app queries that record, it gets an array of both titles back. Now, this brilliantly avoids the catastrophic data loss we just saw with last write wins, but it means you, the developer, have to build complex, intricate logic to merge these siblings back into a single record everywhere a collision might happen. And this brilliantly illustrates what happens when you try to manually merge siblings without a bulletproof plan. It's the classic shopping cart anomaly. Device 1 removes a book from the cart and adds soap. Concurrently, device 2 removes a DVD from the cart. Keep in mind, both devices started with a cart containing the book and the DVD. The databases record these concurrent updates as siblings. Okay, now the application steps in to automatically merge them. If the app uses a naive set union, which basically means the algorithm just asks what's in cart A, book and soap, what's in cart B, book and DVD, it just jams everything together. The algorithm is completely blind to the fact that the user took specific actions to remove items. So look at the result. The merged cart suddenly contains the DVD, the book, and the soap. The items the user explicitly tried to delete have suddenly reappeared like zombies. Section 5, Automatic Conflict Resolution, the magic of CRDTs. So to stop deleted items from magically reappearing as zombies without forcing the end user to manually fix every tiny conflict, we get to the modern, cutting-edge solution for collaborative apps: automatic resolution algorithms. These are explicitly designed to make sure all replicas safely converge to the exact same state, which gives us what's called strong eventual consistency. The big players here are conflict-free replicated data types, or CRDTs, and operational transformation, or OT. You can think of them like a highly intelligent auto-merge. If users are concurrently editing text, one adding a letter, another adding a comma, these algorithms perfectly preserve all those little insertions and deletions. And remember that shopping cart anomaly? CRDTs fix it flawlessly. They do this by explicitly tracking deleted items, using hidden markers called tombstones. A tombstone isn't just deleting the data, it's saving a permanent, concrete record of the deletion itself. So instead of just looking at the final items in the cart, the algorithm remembers the specific action of deleting the book and deleting the DVD. When the merge happens, those tombstones enforce the deletions, ensuring the zombie items stay dead for good. Summary: choosing how you lose or merge data. At the end of the day, building a distributed application is rarely about finding one single magic bullet. It's about looking at these exact strategies and picking the trade-off that fits your specific app.
Let's walk through this matrix to tie it all together. First up, avoidance. You route traffic to one leader, acting like a single database, but it fails catastrophically the second that leader goes down. Then, last write wins. It just takes the highest timestamp to quickly resolve the conflict, but as we saw with that vanishing bank deposit, you get permanent data loss. Next is manual resolution. The database passes the buck, so the app has to merge siblings, but it's super complex and risks anomalies like our zombie shopping cart. Finally, automatic resolution. It seamlessly merges via CRDTs or OT using tombstones, but as that final row points out, even this magic cannot enforce all business constraints.
Which brings us to our final, kind of provocative thought. Even magic algorithms have hard limits. What if you have a strict business constraint, say a VIP list that caps users at exactly 5 items, and 2 users can currently add items bringing the total to 6? How do you automatically merge that? Well, actually, you can't. It is mathematically impossible to resolve that conflict without dropping data. Even the smartest automatic conflict resolution hits a brick wall here, and your app has to make a hard choice about what data to throw away. Keep that in mind and think about how your favorite collaborative apps handle these hidden limitations the next time you're using them. Thank you so much for joining me on this explainer. I really hope it brought some vital clarity to the wonderfully chaotic world of concurrent writes.